This is a talk that is related in spirit with Stavros's and Daniel's talk. So I wanted to, in the spirit of this kind of cross-pollination of knowledge from AI and search, I wanted to just discuss this a little bit and make parallels with their talk. So first of all, who is familiar with deep research? Okay, who has built a deep research agent before? No. So okay, I will explain very quickly. So a deep research agent works in the following way. You have a query. You have some sort of orchestrator that will decide what to do. In this case, it will send it will ask different sub-agents to create queries or sub-queries. They will feed the documents that are found to another set of agents that will summarize the information in these snippets. And then this procedure will kind of go in a loop until the orchestrator decides it is good enough. And then all of these snippets will be fed into another agent, will produce the actual result. So each of these sub-agents is a prompt. And the question is how can you, or sorry, the parallel from Stavros' talk is that this, I think, is something like the tools that the agent can use to optimize search. But in this case, we're optimizing deep research. So the question is, how can you make this really good, apart from like just manually changing the prompts, which we have done before. So this is based on two papers. One is called TextGrad. So TextGrad has some parallels with gradient descent, like in machine learning. Not going to go into detail, but basically the prompts are mutated in a specific way. And you can see here how the evolution of the different modules change. So a module, in the case of the deep research, is one of the prompts for one of the sub-agents. So you can see that it kind of specializes in one area and kind of digs deeper. But from what Charlie asked in Stavros' talk was what happens when you have multiple things that you can do, and maybe one change affects the other change and so on. So there is this another approach which is called a JEPA, which stands for generative Pareto, which combines this kind of genetic, combines genetic algorithms to kind of mutate these prompts, and Pareto frontier to select the best candidates to evolve the system. So in this way, if you look at how the evolution looks in this case, it kind of changes from like module to module, and is able to find like the optimal solution without breaking your previous optimization. So very gross simplification of how this works. So you have a query, you have this kind of deep research agent that has an answer. You create some kind of feedback, LLM as a judge feedback, which then you pass to an optimizer that then will mutate the prompt. And then basically you add this new mutated set of prompts into the pool of agents, and then do kind of this selection process and go into a loop. So very, very hand-wavy, I know, but the results are as follows. So this is based on a benchmark. So we have two starting points. One is like a minimal prompt, which is this one that is like very simple, just says answer the question. And this other one is like the one that took us like 1 year and a half to create manually. So the idea is that by using these two methods, so this is TextGrad, this is a JEPA, you can see that we are able to create from the very basic one to this one, so like a big improvement. And then from the kind of manually created one to here, which is a little bit less improvement. And you can compare the gray one, which is the just if you put the prompts into OpenAI. So the kind of takeaway here is that JEPA, it has better performance, which tells us that the way we select the candidates is very important. And yeah, connecting back to Stavros' talk is that how you actually evolve the system in a way that you don't remove the previous gains. So anyway, so next steps, which I'll not discuss, is how you can do that without a benchmark, because before we use a benchmark. So there are some other interesting ways, but I'm not going to details of that for now. Thank you.
Thank you.